So I'm really thankful for this. And well, the first question is what I'm doing here, giving this panorama. When Marcello invited me, I said yes, and then immediately I realized that, oh my God, is this my topic? And then I told him, are you sure? He said yes. So I'm making an effort to get close to the movement of the electrons, as he suggested, and I take as a starting point a paper by Urs Frauenfelder, which is related to movement of the electrons, and this takes me to discuss some of the current problems in symplectic topology. So I'm going to compare two different motivating examples here. Well, first I look at the Calogero-Moser systems, even in spin Calogero-Moser systems. I can think of this as a many-body problem with some particles which are repulsing that can be on a line, on a circle. These systems have been generalized to Lie groups and to any kind of representation theory in an abstract format. And well, what it's important is that they are integrable. And integrability gives us a good hint that things cannot be too much chaotic. Indeed, the orbits have to lie on a Liouville tori or cylinder. Usually when we talk about down-to-earth problems, these are going to be cylinders. And well, this doesn't happen if you have integrability, then essentially you have some kind of order. You have some first integrals, okay, that commute, and the movement of your particle can only happen in those restricted to those hypersurfaces, to those set of surfaces or manifolds sets which are half the dimension of your manifold. This is not the case of the helium atom. This is an old, indeed, this is a paper by Frauenfelder, which he posted this last year, 2020. But indeed, this is based on an old study. I don't remember the author, by a German author, about the movement of, we have two electrons on a line on the same side of the nucleus. This is the case of the helium atom. Therefore, we have mutually repulsing electrons attracted by a positive nucleus. We're in a very close situation to the Calogero-Moser, apparently, but we are not, because this system is non-integrable, okay? This would be a special case of a three-body problem, which is non-integrable and which shows chaotic features. So one of the things that are common in Hamiltonian systems that are integrable is the existence of periodic orbits. One tends to think that when you throw a particle, it will come back. Of course, we are interested in having periodic orbits because sometimes this could be a satellite, as we will discuss in some slides. So Frauenfelder considered the problem of existence of periodic orbits in the case of the helium atom, and he just found one, which is called usually the frozen planet configuration, because when you have one of these electrons that has periodic orbit, the other one doesn't move, it's frozen. So, well, he proved this by hand, just by integrating some equations and proving that you can only have one solution. And this is a nice paper on the arXiv where he recovers some old computations too. Okay, and one of the features of this example of Urs Frauenfelder is that you cannot apply techniques which are sophisticated techniques to fish this existence of periodic orbits, which have been very popular in the business of symplectic topology, which is Floer theory. Okay. And why can't you apply those techniques? Because essentially the problem that this example has, and many other examples in physical systems, is that they are non-compact. So the purpose of my talk is to see how to address the problem of existence of periodic orbits when you have a non-compact manifold, and sometimes these non-compact manifolds can be compactified to something that is singular. Okay, can you hear me?
Yes,
okay.
Yes.
Okay. I mean, okay. If there is something you don't understand, please stop me, because of course this is like I have here 29 slides, many pictures, but I mean I can stop any moment. So what I wanted to describe to you is that this Morse theory, this Floer theory, whose purpose is to fish periodic orbits, is totally inspired by the theory of Morse. Morse theory, all of us have heard about it. The condition of Morse is a condition that is generically used. And well, Morse theory, indeed, the idea of Morse was to reconstruct your manifold from the critical points of a function. Okay. Now, what happens? This function in Morse theory is a function on a finite dimensional space, and things are well understood. You can read the topology from the singularities. Here we have a torus, and if you take the height function, then you have 4 singularities of different type. You have 2 elliptic singularities and 2 hyperbolic singularities. And from the information that these kind of singularities give to you, you can learn things, and you can totally reconstruct the topology of your manifold. This was a source of inspiration for Andreas Floer, because if you can try to apply these ideas for critical points of now not a function but a functional. This is the action functional, and this is defined on the loop space. So this is the set of C-infinity functions of S1. So let's say a gamma here, okay, it's a circle. And why we should consider this loop space and why we should consider this action functional is because Rabinovich proved that the critical points of the action functional are in one-to-one correspondence with the periodic orbits. And there are some constraints that I'm not talking about constraints, but here I used an extension to a disk. So essentially, this works very well if you have, for instance, that the second homotopy group of your manifold is 0. Okay, so you have some conditions under which this holds. And this was a brilliant idea of Rabinovich. I mean, this is indeed the origin of Floer theory. Now here, the critical points, you have critical points of something that it's not a function, it's a functional, and you have identified them with periodic orbits of your system. Okay, so that's the condition. All you have to do is to consider this action functional when you have something that is called Hamiltonian, and here you have an extension of omega, which is what is called your symplectic form. I will define in 2 minutes. And then you look for the critical point, and then you have periodic orbits. Then Urs Frauenfelder does this in his paper, and this is the case of the helium atom, and he writes down, and you get some equations, and essentially he fights with these equations. Okay, one of the good news about how you can put this information of periodic orbits and critical points inside a complex, okay, such that these critical points or these periodic orbits are the generators of your complex. This was the idea of Floer, to construct a complex associated to this problem. And the surprise, well, I mean, of course, why periodic orbits? Because, well, first because we want to come back, and secondly because it's a way, as Poincaré put it, to understand. It's a first approximation to understand the dynamics of your problem. And in a way, periodic orbits like describe this kind of islands that Poincaré is talking about. And which kind of systems? I already said we are considering conservative systems, and for a geometer, these are Hamiltonian systems. So for somebody thinking about conservative system, is the person who throws a big object, okay, a heavy object, and then you have potential energy converting into kinetic energy. Okay, and for us geometers, these would be Hamilton's equations. And well, here we have the sphere. Rotations of the sphere are an example of Hamiltonian system. A little bit of language, because we should a little bit, these panorama talks introduce the language, and this is going to be good for Sonia after. What is a symplectic structure? This is a non-degenerate closed-to form. And this non-degeneracy is giving you an isomorphism of the cotangent bundle and the tangent bundle, which has as a consequence that whenever we plug one form, we have a unique solution to this equation. And if this one form is the differential of a function, then this vector field is called Hamiltonian vector field. What makes symplectic geometry so attractive if we compare it to Riemannian geometry? Well, the first important information is that there are no local invariants, and that's something that is quite funny. So when we think about Riemannian geometry, of course, curvature is a local invariant. And when we think about symplectic geometry, there are no local invariants. Locally, all manifolds look like a cotangent manifold. That's indeed what is going to be the model, the local model for a symplectic manifold. Okay. And then what's interesting is that in Darboux coordinates, the flow of a Hamiltonian vector field corresponds to Hamilton's equations. There is this is the condition that that omega is a non-degenerate closed-tube form imposes an important restriction on the dimension of the manifold. This has to be even, but we have a not-dimensional equivalent which appears in nature when you consider a symplectic manifold and you take an hypersurface, such that it admits a vector field which is transverse to this hypersurface, and this vector field is a Liouville vector field. So it preserves the symplectic form. Then if you have these conditions, what happens is that when you restrict this vector field, when you contract this vector field with this symplectic form, you get a one form alpha, and this one form is contact in the sense that it's maximally non-integrable. The condition of maximal non-integrability is equivalent to the fact that alpha wedge the alpha to the n defines a volume form. And then the dynamics that are important here are not only the Hamiltonian dynamics, which makes sense, but also the Reeb dynamics. And the Reeb vector field is defined by these two conditions here. So this is a summary, 1 minute summary of what is important in dynamics, in symplectic and contact geometry, and what people care about. People care about Hamiltonian and Reeb dynamics, essentially. So you can ask this question of periodic orbits, and now you ask the question to Hamiltonian vector fields and Reeb vector fields.
So Eva, what are the pictures above?
Yeah, the pictures above are to distract the potential people in the audience. That, well, the first one is the camel. This is the symplectic camel. This is an important theorem that tells that you cannot put a camel go through a needle, and this has to be this has to do with non-squeezing theorem, one of the important theorems in symplectic topology. Today I will not talk about non-squeezing. This one is a guy who is perplexed, looking at himself in the mirror. So this is a joke. And this one here corresponds to the standard distribution. Okay, if you take on R3, okay, you take as one form, take the standard coordinates x, y, z, and you take as one form dx plus y dz. Okay, this you take as alpha this form. Then this alpha satisfies this condition here. That's easy to see because when you do the wedge, you get dx wedge dy wedge dz. And then what happens is that the kernel of alpha is maximally non-integrable. That's why it follows all possible directions. So that's a picture of the kernel of alpha when you move the point on R3. Okay? More questions? Okay. So there are two guiding conjectures in the literature that essentially concern periodic orbits. Let's say one of them, I chose one of them for contact manifolds. Bayesian conjecture tells that the Reeb vector field of a compact manifold has to admit at least a periodic orbit. When Alan Bayesian did this conjecture, he was considering indeed the case of R2n and restrictions to a convex hypersurface on R2n. That was the origin of this conjecture. This has been proved to be true in a number of situations, in particular on all three compact contact manifolds. And the Arnold conjecture is about existence of periodic orbits for time-dependent Hamiltonians on a symplectic manifold. And if we don't assume that the Hamiltonian is time-dependent, this condition indeed can be read from Morse inequalities. What are the beta k? Beta k are the Betti numbers, okay? So the dimension or the rank, as you want to think of them, of the homology groups of your manifold. So essentially, if you don't assume that your Hamiltonian depends on T, essentially the observation that I did before already gives you that Morse inequalities and the identification of periodic orbits. Let's say Morse inequalities give you this with respect to fixed points, which would be a particular case of periodic orbits. And if you want, if you have a time-dependent Hamiltonian, then this gives you a lower bound of the number of periodic orbits you can expect for your Hamiltonian system. So essentially, this have been, indeed, Arnold's conjecture was indeed the conjecture that motivated Andreas Floer to build up all this theory about Floer homology. I don't want to be very, very technical. It doesn't make sense in this conference, but somehow, if you don't understand this slide, nothing happens. You can understand the whole talk, but I just want to highlight that in this complex, as I said, the generators are periodic orbits. Therefore, solutions of these equations are critical points. So you want to find periodic orbits of these equations. So what you need to do is to take critical points of the action function. And then what's very important in Morse theory is that, for instance, imagine that you have the torus, you have the two critical points, for instance, the hyperbolic point, okay, and the point in the top. An important thing, I'm moving my hand and I don't know if you see me. I don't know if my camera is working. Do you see me?
No, we don't see you.
Yes, I
Okay.
don't, but we see
So I have been doing all kind of body language, totally useless. Oh, I'm sorry. Okay. So that's terrible. So I'm moving my hands uselessly, but well, I'm sorry. So imagine that you have the height function on the torus, okay? And now you want to travel from the top critical point to the hyperbolic, to the first hyperbolic point, okay? I mean, we had these slides. I'm doing something very dangerous, which is moving slides here and putting this here. I'm going to go from here to here. And a way to do this is to take a Riemannian gradient, okay, and to take the flow of the Riemannian gradient to travel from this point to this point. In the same way, we have to have this kind of picture in the Floer case. And in the Floer case, this is much more difficult because you deal with infinite dimensional objects. But you have to think that then what defines the symplectic, this Riemannian gradient that doesn't depend on the data that you put, indeed ends up being the Floer equation. Okay, so the gradient lines that connect these critical points that correspond to the periodic orbits would be precisely are giving us solutions of the Floer equation. So this Floer equation, here we have some element I didn't define, which is a complex structure, but I'm not going to define. But what's very important about this Floer equation is that the solutions are under control. The solutions of these partial differential equations must satisfy some condition that their energy must be finite. The energy is this integral, okay? And this condition is met, and this is a hard proof, if your manifold is compact. But if your manifold is non-compact, this energy may not be bounded. That's a problem that we have if we want to extend all these apparatus to non-compact set.
Eva, could I ask a question, which I should
Yes.
probably already have asked the last slide? You were talking about periodic orbits of these time-dependent systems. Do you require these time-dependent systems to be periodic in time, or how do you define it?
No. Yeah, that's a good question. No, we meant that I mean, we think of this time as a parameter.
Ah, okay.
But okay, I see what you mean. That in some of the formulations we require that this is that this is time periodic in T2 in order for this equation to make sense, but not in the place where you mention it, but later on.
Okay.
It's a technical issue. Yeah, there is some of this, but it's not important. Yeah, I mean there is a condition, but what you want what I say is that the periodic orbits, we want these to be as solutions not in T, okay? T's are like a parameter, but sometimes we need to impose that is periodic in T so that some equations make sense. You are right. I'm being quite general, panoramic, not concrete. Okay, so in this business, this was an important moment in the theory, and a little bit a deception moment for Andreas Floer, because you construct a complex that depends on a Hamiltonian, on a function, and then what turns out that it doesn't depend on anything. It doesn't depend on the Hamiltonian, it doesn't depend on the symplectic form, or on this complex structure that I'm going to keep as a mysterious ingredient of this, because I don't want to enter into technical issues. So essentially, you can prove that Floer homology of a manifold is isomorphic to Morse homology, or if you want, singular homology. So the standard homology of the manifold. And a good corollary of this is that this proves the Arnold conjecture for a wide class of manifolds. You need to have the conditions that pi2 of your manifold equals 0, for instance. You need to have such a condition. There are some generalizations without this condition, but this gives a direct proof of the Arnold conjecture. But this is a moment in which Andreas Floer was not so happy, because you construct a complex, and at the end of the day, this complex is the complex you already had at the beginning, which is the structure of your manifold. So somehow this is telling you that there's not so much influence on your Hamiltonian system itself, because let's say the singular homology or the standard cohomology of your manifold, you can think in these terms, is just given by the topology of the manifold, not by this additional energy or this information that you have from your physical system. But a good corollary of this is that you can prove the Arnold conjecture. And now what I want to say is why, and I'm not going to be very technical because it doesn't make sense, but I will work with an example, why it's convenient to extend Floer homology and these nice ideas of critical points identified with periodic orbits to not the non-compact setup. Okay. Well, here I give you 4 possible answers, and my favorite one is the last one. The first one is because some non-compact symplectic manifolds can be compactified as compact manifolds, but maybe not symplectic. Maybe your compactification is introducing some singularity. We will see this in an example. And these singularities indeed are not, I mean, of course, you can always include a singularity in a problem if you want by making an artificial change of coordinates. But what happens is that these singularities often appear as regularization transformations in celestial mechanics. So there is a reason to perform those changes. And also they make sense on certain manifolds with boundary. And the fourth one is my favorite one. Why not? So if you see all these people here in this picture are smiling and they are working with these problems with singular compacts. So they are happy. So I want to be in this group of happy people, and I'm here. This is me with Anarita Pires. So I have to give some definitions about what I mean by singular. And Marcelo or Andreas, you will tell me how bad I'm doing in terms of time, because how much time I have?
Formally 6 minutes.
6 minutes, okay. Then, well, in 6 minutes, I want to convince you with an example. I'm going to consider the restricted free-body problem, okay? And I want to show you that we have some singularities in this problem. Well, the restricted free-body problem, it's a particular case of general three-body problem, like these many body problems we discussed at the beginning. But these bodies are attracted by gravitation. So this is what we call gravitational free-body problem. Okay. So here we're going to assume that we have one of the objects is a spacecraft, and the other two are maybe the sun or the moon or the Earth and the moon, for instance. And we have a spacecraft, and we want to find, the trajectories of this spacecraft. So what we do is to assume, of course, that the spacecraft, the mass is almost 0, so it doesn't affect. But this spacecraft, okay, we assume that the primary and the secondary move according to Kepler's law for the two-body problem, okay? And then there is an assumption that, this restrictor three-body problem, there are several classes, like restrictor planar three-body problem, circular, etc. We assume that we are in the circular planar restrictor three-body problem. When we are in the circular planar restrictor three-body problem, okay. My computer is like playing jokes on me. Okay, you can see this slide, right? So we are in the circular problem. This is the potential. This is, we are normalizing the masses to mu. So the Earth has a mass 1 minus mu, and the Moon has mass mu, okay? And this is the potential. And then the Hamiltonian, of course, is the total energy, so kinetic plus potential. And because we are assuming that you are in the circular case, it makes sense to perform a polar change of coordinates that you can perform. And now it comes the interesting thing. McGehee considered interesting to consider this change of coordinates. We consider that the radius is 2 over x squared. And of course, this doesn't make sense when x equals 0. Okay, but x equals 0 in this particular problem corresponds to what people in celestial dynamics call infinity. Okay, so people in celestial line at infinity, x equal to 0. So many works, people in celestial mechanics want to see what happens when you are close to infinity. And what they do is to use the symplectic form as much as they can, but then there is a kind of silence when x equals 0. Why? Because, the symplectic structure becomes a singular object. And when x equals 0, this is no longer a smooth form. You can think of this as a Poisson structure. If you invert the matrix, you have a perfectly well-defined bivector field. A bivector field that satisfies a condition, integrability condition, and therefore is a Poisson structure. You can think of this guy as a Poisson structure, but it's a pity because it's almost a symplectic structure. It's a symplectic structure everywhere except for x equal to 0. So essentially, we're interested in this kind of systems because they appear naturally, and this is what we call singular symplectic. Sometimes you may also have some duality, but I'm not going to talk about it. And then it still makes sense, this idea of restrict to an hypersurface. And then the question is, when you restrict to an hypersurface, if you have this condition that the Liouville vector field is transverse to it, you may inherit a singular contact structure. And then the natural question is, do you have the same kind of conjectures here in the singular business? And this question makes also sense in the non-compact setting, because in a way, here, when we are considering this example, we may take out the line x equal to 0, okay? And then what we have is a non-compact symplectic manifold. We could consider, for instance, a sphere, and we could induce such a singularity on the sphere, okay? So it makes, so what I want to say is that now we try to extend this picture. And then the natural question is, what do you mean by periodic orbits in this singular setup? Do you want to consider some kind of orbits that have some behavior as the first talk we saw today, that get to the singular stratum? Which kind of singularities you want to consider? Then, the first thing I'm going to do now here is to describe for you some work of, very quickly in 1 minute, of Frauenfelder and several people, Patternet, Van Coert, and I'm forgetting one, sorry, where they use this kind of theory. They use the Bunsen conjecture that holds in dimension 3 to prove that there exist periodic orbits for each level set, for each energy value of the close to the first Lagrangian point of the restrictor three-body problem. I'm going to tell you how they do this. Well, first, they introduce some interesting change, which is that the Hamiltonian here depends on time, and if you take rotating coordinates, then it doesn't depend on time. Okay. Now, what they do is to look, something that is very well known is that the critical points of this Hamiltonian are the Lagrange points. Okay. Then what they look is what happens close to you take the level set of energy of the first Lagrange point, and they analyze what happens close to this level set. And the question is, are there periodic orbits? How do you find them? And then a nice application they find of Weinstein conjecture is to prove that for any value of the energy, okay, that is below the first Lagrange point, the problem, which is not exactly the initial problem, the restricted three-body problem, but the regularized planar, because they use Kepler's regularization, the regularized planar circular restricted three-body problem has a closed orbit with energy C. That's what they prove. And now the question is, what happens if now we consider making computations in this model and we add this McGehee transformation? Okay, that's something we did. I'm going to skip this. That's something we did with my student Cedric Ohms last year. And well, first there is a way to make formal sense of this. These are called B structures, and they appear already in the work of Melrose. Okay, and what we did is to do exactly this, to impose the McGehee change of coordinate, and then we proved that there are infinite periodic orbits on the critical set of this problem. So let's say this is a step forward trying to understand the business of periodic orbits when you have non-compact or critical sets. You can do much, and the interesting thing about this is that here the critical set still is non-compact, it's a cylinder, but the computation was hands-on. Another thing you can do is this happens, the critical set has infinite periodic orbits for any of these critical contact manifolds that we call VM contact manifolds. That means that you have this kind of singularity of order M. And this happens whenever it's compact. And the proof is just the observation that the critical set itself is a symplectic manifold, and that the vector field, that the Reeb vector field indeed restricts to a Hamiltonian, and then the proof is automatic. Then the natural question, we had examples without periodic orbits on M minus Z, and do we have periodic orbits close to Z? One thing we could do is to use a technique by Hofer to prove the existence of periodic orbits whenever we have a condition related to a symmetry condition that here we called R plus invariance close to the critical set. So essentially the mantra is that when you have a non-compact manifold, but you have this R plus invariance, you can still apply many of the techniques of Floer. A different business that I have no time to talk, so I'm going to leave like this, is to study this kind of orbits that go to the singular strata that Bellotto was talking about in his first talk. And the question is, should we consider this guy here, this semicircle, as a critical periodic orbit? And what's interesting about this question is that if you have escape orbit in celestial mechanics, that's exactly what happens. You have an orbit that goes to infinity, this line could be infinity, and then what can you say? Can you prove existence of these singular orbits? We did it by hand with Cedric and my colleague Daniel Peralta Salas by using an interesting correspondence between contact geometry and fluid dynamics that I will not go into. But essentially, if you want to say something about the Reeb vector field, you can use strategies in Beltrami vector fields. And what's interesting is that this function that you have, the Hamiltonian function, indeed, it's an eigenvalue of the Laplacian. And this was giving you an important information that at least you have this number of escape orbits. Whenever you have a situation, a particular situation. So, and just to finish, because I don't have time, I'm going to finish with this last slide. This last slide tries to say some other context in which you have this non-compact business. The ones who started working in this are Frauenfelder and Felix Schlenk, who proved that if you have a symplectic manifold with contact boundary, then you have such a situation. But then you need to take some restriction of the Hamiltonians. We have been mimicking their work, and we have a similar result for this kind of manifolds when the restriction is a co-symplectic manifold that I didn't explain at all today, but corresponds to this b-symplectic business. I'm going to stop here. I'm sorry for taking time. I'm going to stop sharing.